Hi everyone, this is your last lesson video for the week. Woohoo! What we're going to do today is we're going to talk about using something called the ratios of similarity. So we'll get to that in just a minute, but the first thing I want to do is review with you a few things we know about dilations. Dilations are a type of transformation. And remember, we said they're not a rigid transformation because we're changing the size, but they are still a transformation because they move an object to a new place and change it. Dilations produce similar figures, and we'll talk about that a little bit more in just a minute. When we perform a dilation on an object, side lengths change, but angle measures stay the same. And the scale factor that we use to shrink or enlarge or sometimes keep the same size figure tells us how we are changing things, by how much we are enlarging or reducing it. So now I'd like to move forward with talking about similar figures and these ratios of similarity. Similar figures are two figures that have the same shape but different sizes. So when we start with a figure and we enlarge it or shrink it by a certain scale factor, we are creating another figure that has the same shape, but that is a different size than the original, kind of like these two rectangles right here. We're going to examine those in just a minute. Now, when we dilate a figure, when we create similar figures, there's always something called a ratio of similarity. If there is a ratio of similarity, you know the figures are similar. And if you know figures are similar, you know there's a ratio of similarity that you can use to help you find other side lengths. What is this ratio of similarity? It's just a ratio between any pair of corresponding sides in similar figures. So when two figures are similar, the ratios of similarity will be equal if set up the same way. So what does this mean? Okay, first of all, a ratio is just a fraction where we are comparing two quantities together. How do we set up a ratio of similarity between two figures? Well, that means we're just picking corresponding sides between the two figures and comparing them to each other. So for example, this side length of 2 could compare to its corresponding side length of 7. And this side length of 6 in the smaller rectangle is going to compare to its corresponding side length of 21 in the larger rectangle. Now remember what I said before. If we have similar figures, those ratios of similarity should be equal to each other no matter what pair of corresponding sides I chose to compare. In other words, if these figures are truly similar, then 2/7 should be equivalent to 6/21. How do we check this? Well, we either look to see if we can take one fraction and reduce it to make it look like the other fraction, or we can write out the decimal equivalent of each fraction and see if they are equal to each other. If we are going to reduce the fractions, if we take 6/21, 6 and 21 are both divisible by 3. If I take 6 and divide it by 3 and 21 and divide it by 3, I get the equivalent fraction 2/7. So by reducing one fraction, I was able to produce the other. Those ratios are equal to each other, which is in line with what we expected since I told you these rectangles were similar. The other thing we could do is write out the decimal equivalent for each fraction. If I take 2 and divide it by 7, I get 0.286 rounding. And if I do the same thing for 6 divided by 21, I get the same decimal, 0.286, when I round to 3 decimal places. So again, I've shown that the ratios of similarity are equal for this figure, and that confirms that the two rectangles are similar to each other. Now, what happens if I say that I set up one ratio as 2/7 and the other ratio is 21/6. If I take a look at these, 2/7 has a decimal equivalent of 0.286, and 21/6 has a decimal equivalent of 3.5. So here I've compared sides between the two rectangles, and they're not equivalent to each other. What happened? Because my rectangles are supposed to be similar to each other. Well, the problem is we weren't being consistent. Take a look up above. I said consistency matters when you're making these ratios, okay? If I write my first ratio as 2/7, I'm comparing a side in the small rectangle to a side in the large rectangle. If that's how I start making my comparisons, any other ratios of similarity that I set up have to follow that same pattern, small over large. And this one right here did not. I did large over small. And so that's why it makes a difference. So let's see how we can use these ratios of similarity to help us find missing side lengths in figures that we know are similar. So each pair of figures below is similar. We're going to use equivalent ratios of similarity to set up proportions to solve for x. So take a look at our two rectangles for part A. In the smaller rectangle, we know two side lengths, and in the larger rectangle, we know one side length and we're looking for the other. We can set up equivalent ratios of similarity to solve for x. Since we know the rectangles are similar, every ratio of similarity that we set up should be equal to each other as long as we follow the same pattern. So for example, if I take the side length of 2 in the smaller rectangle and compare it to the side of 4 that it corresponds to in the larger rectangle, that should equal the side length of 6 in the smaller rectangle compared to x, which is the side it corresponds to in the larger rectangle. So again, every ratio I'm setting up is taking a side from the smaller rectangle and comparing it to its corresponding side in the larger rectangle. If we cross multiply, we get 2x is equal to 24, and dividing by 2, we get x is equal to 12. So the length of that second side in the larger rectangle is 12. Take a look at the next one. If I compare x in the larger figure to the side length that's 6 in the smaller figure, those are corresponding sides. And then if I compare 4 to 3, another set of corresponding sides. And each of these ratios takes a side in the larger figure and compares it to its corresponding side in the smaller figure. Cross multiplying gives me 3x equals 24, and dividing by 3 tells me that x is equal to 3. And for the last one here, it appears that we're missing some information in the larger rectangle because we know that the side length of x corresponds to the side length of 21 if we're taking x from the smaller rectangle and comparing it to 21 in the larger rectangle. But then if we take the side length of 3 in the smaller rectangle, we don't know what this side is yet in the larger rectangle, but we can figure that out. If the perimeter of the entire rectangle is 60, remember that comes from taking 21 times 2 plus, we'll call this other side here y, 2 times y, because there's 2 of them over here, that equals 60. And so we can solve this equation and figure out what that other side length is. 2 times 21 is 42. And if we subtract that from 60, we get 18. So that means 2 times y is equal to 18. And so y is equal to 9. So that side we're looking for is 9. And then, again, we can cross multiply and solve. 9 times x is equal to 63. And if we take 63 and divide it by 9, we get 7. So x is equal to 7. The last problem is asking us to take a look at what happens to the perimeter and the area of a figure when we enlarge it, or if we were to shrink it. So in this case, we're starting with this rectangle, and it first asks us what's the perimeter and the area of this rectangle. Don't forget that opposite sides in a rectangle are congruent. So if we were to take 2 times 7 plus 2 times 3, we'd have 14 plus 6, which gives us a perimeter of 20 inches. Then for the area, it's length times width, or 7 times 3, which is 21 square inches. Now it wants us to enlarge the figure by a scale factor of 2. So remember, enlarging it by scale factor of 2 means we're doubling all the dimensions. So instead of the length and width being 7 and 3, they are now 14 and 6. So what's the new perimeter? Well, we now have 2 times 6 plus 2 times 14, which means we're taking 12 plus 28, which gives us a new perimeter of 40 inches. What's the new area? Well, to find that, we need to take length times width, or 6 times 14, which is 84 square inches. And so the final question asks us, what do we notice about the perimeter and area in the new figure? So in other words, we started with a perimeter of 20 and an area of 21, and after the enlargement, we have a perimeter of 40 and a perimeter of 84. What's the connection between the new perimeter and area and the scale factor? Well, let's take a look at perimeter. The perimeter of the old rectangle was 20, and the perimeter of the new rectangle is 40. The connection between those two is we're just multiplying the old perimeter by 2. So we're just multiplying it by the scale factor. Let's take a look at the area, okay? The area of the old rectangle was 21 square inches, and the area of the new rectangle is 84 square inches, okay? What's the connection there? Well, to get from 21 to 84, we actually have to multiply by 4, which is 2 squared. Perimeter is one-dimensional, so we only have to multiply by the scale factor once when we increase a figure. Area is two-dimensional, so that scale factor applies to the length and the width. It's applying to a power of 2. So we have to square the scale factor and then multiply the old area by that to make our new area. Here's another example. Let's say we have figure A that has a perimeter of 15 centimeters and an area of 14 square centimeters. And let's say we are enlarging figure A by a scale factor of 4, and we're forming figure A prime. What would be our new perimeter? And what would be our new area? Well, for perimeter, all we do is we take the old perimeter and multiply it by that scale factor. Scale factor affects perimeter once. So we're taking 15 times 4, and the perimeter of figure A prime would be 60 centimeters. Because the scale factor affects the area to the second power, we would take the scale factor of 4 and square it and multiply that by the original area. So in other words, I'm taking 14 and multiplying it by 16 to find the new area. The area of figure A prime would then be 224 square centimeters. If we want to see how this works when we are using a scale factor less than 1, or when we are shrinking an object, in this example, we have figure B having a perimeter of 30 inches and an area of 50 square inches. If I want to use a scale factor of 1/2 to reduce the size of the figure, how does that affect perimeter and area? Well, again, scale factor affects perimeter once. So to find my new perimeter, I'm taking the old perimeter and just multiplying it by that scale factor. 30 times 1/2 gives me a new perimeter of 15 inches. If I want to see how my area is affected, then what I need to do is multiply by my scale factor raised to the second power, because area is affected to the second power by that scale factor. If we square 1/2, that's 1/2 times 1/2 or 1/4, that means we're multiplying the old area by 1/4. And 50 times 1/4 gives me a new area of 12.5 square inches. So to wrap up this lesson, you have a short assignment to do for me. And when you're finished with that assignment, please take a picture of your work and upload it into this assignment tab. If you have any questions, please don't hesitate to send me an email and let me know. Have a good weekend.